Now, we're going to keep on examining Gibbs free energy. And I had told you a while back that if you took this equation, delta G equals delta H minus T delta S, that this equation would be true without the circles and with the circles, either one. One being in standard state conditions and one not being in standard state conditions. What I know about students is they struggle with what the difference is between those two things and what delta G is really telling you. So we've got standard state conditions and not standard state conditions. We're going to go through and have a lot of questions for you to answer considering a reaction and thinking about the magnitude of delta G, what it does, when is it standard state, when is it not standard state. And hopefully by the end you'll start getting a grasp on the difference between these two. Okay, so I told you that already. Let's refresh your memory what the standard state conditions are. If it's in standard state conditions and it's a gas, the pressure is going to be 1 atmosphere. Okay? If it's in solution, it's 1 molar. Those are the standard state conditions, and the tables are always reported at 25 degrees Celsius, so you can talk about a standard delta G at some other temperature if need be. Okay? Now, if everything is at 1 atmosphere, that's standard state conditions. Every gas in there, okay? Most systems are not going to be at equilibrium when everything in there is at 1 atmosphere. Or if we put things in solution and everything in the reaction is at 1 molar, it's probably not going to be at equilibrium. That would be very, very, very unusual situation. So the system under standard state conditions means all reactants and all products are already in there at 1 atmosphere, and we're going to be able to determine whether the reaction is going to go in the forward direction spontaneously or the reverse direction spontaneously. And consequently, I said that the delta G standard in tables are at 25, but if you needed a temperature, a value for delta G that's not at 25, you use this. You come up with standard delta H's from the table, standard delta S's from the tables. These things don't change significantly with temperature. You put in your new temperature and you get a new delta G. This does change significantly with temperature. Okay? Now, what we're going to do is examine this reaction. I've got it drawn here for me so that I can manipulate it and play around a little bit with it. So let's first state that our system is at equilibrium. Everything in the reaction is at 1 atmosphere. Now, what's the reaction? The reaction is H2, it's a gas, plus Cl2, it's a gas, going to 2HCl. Each thing is a gas. So there is my H2, there's my Cl2, and there's my HCl. And everything at the beginning of this reaction is at 1 atmosphere. I've got those conditions mentioned right there. Now, if the value of the standard delta G value is a negative 190.5, what that is telling me is that if this reaction started with everything, all reactants and products, at 1 atmosphere, the value of delta G would be a negative 90.5, and what does that tell you? You choose your answer. All right, well, the answer is A in this case. Why? Well, a negative delta G says it's spontaneous in the forward direction. So this is a snapshot. Telling me what delta G is under standard state conditions is a snapshot of a condition. It says at this condition, it is going to proceed to the right. That's it. That's all it tells me. But I have to start with this set of conditions, everything at 1 atmosphere. Okay, so let's think about what this is going to do. When the equilibrium is established, eventually it's going to get there. It's going to proceed to the right until the forward and the reverse reaction are happening exactly at the same rate. When that happens, what is the pressure of HCl going to have done? Will it have increased? Will it have decreased or will it have not changed? Well, certainly if it's proceeding to the right, you're going to be making more HCl. So some of the H is going to get used up, some of the Cl is going to get used up, and some of the HCl is going to be formed. So let's say it shifts a little bit. I don't know how much it's going to shift to get to equilibrium, but let's say we use up one of those, that's the H2, and we use up one of those, that is a Cl2. What are we going to make? Well, when you use up one of these and one of these, you're going to make two of the HCl. So I'm going to make one HCl and I'm going to make another HCl. So now I have two more molecules of HCl than I had before. All right? If you've got more moles in this rigid container here, the pressure of HCl is going to increase. What about the total pressure? What will happen to the total pressure? Now remember, the total pressure would be the pressure of H2, the pressure of Cl2, plus the pressure of HCl. What's going to happen to the total pressure? Well, it is not going to change. It is going to stay exactly the same. Let's think back to our picture. I drew in two more HCl's, didn't I? But I took out two molecules. The number of molecules did not change. Okay? And so the pressure is not going to change. When a reaction is shifting right or left, and there's the same number of moles of gas in there, it is not going to change the pressure of the container. So that's just kind of a refresher about the effect of a shift on pressure if the gas molecules are the same on either side of the equation. Okay. This is a tricky one for students, so I don't want you to answer too quickly. We started under standard state conditions. Am I still under standard state conditions here? Standard state conditions were when everything was 1 atmosphere, and then it shifted and it produced some more HCl. It went to the right. Okay? Eventually it's going to get to equilibrium. Okay? What happened to the standard delta G once equilibrium was established? Did it increase, did it decrease, or did it stay the same? All right, this is going to blow your mind for some of you. It doesn't change. Standard delta G doesn't change. It is a snapshot of a time in history when everything was at 1 atmosphere. That was before I messed with this picture. The picture you see on your screen is when it was under standard state conditions. This delta G is when it's in standard state conditions. So if this reaction goes off and journeys into a place that's not standard state conditions anymore, that doesn't change the fact that if it were in standard state conditions, it would have this value. So standard state conditions is, I'm taking a picture of you right now when everything is at 1 atmosphere, that's your value. That's not going to change. That picture of time of when everything's 1 atmosphere is always going to be this value. Now, as soon as it starts shifting and going to trying to get to equilibrium and concentrations are no longer 1 atmosphere, pressures are no longer 1 atmosphere, then things are going to change and we're going to have different values. Okay? So eventually it's going to get to where it hits equilibrium. All right? It started here. This was a snapshot at the beginning, which is the picture you see there on your screen. This is the beginning point when everything was at 1 atmosphere. It starts working its way to equilibrium. And when it gets to equilibrium, it's going to have a value of delta G. All right? What's going to be true? Will this, the delta G, once equilibrium is established, will it be positive, will it be negative, or will it be equal to 0? Well, the delta G is equal to 0 when you're at equilibrium. Okay? So delta G is equal to 0 when you're at equilibrium. So what happened to our delta G? As soon as it started shifting and you started producing more of this came up a little bit. And it shifted and I produced a little bit more of this and it came up a little bit more. It shifted. Now not the delta G standard, it's not changing, but the delta G is coming up until eventually it gets to equilibrium and the delta G is equal to 0 at that point. So the bottom line, this doesn't change. This is where it was at the beginning when everything was one atmosphere. This is a snapshot of a single condition. Very often a reaction is not under standard state conditions. If it's not under standard state conditions, we take away that circle. We're talking about non-standard delta G, and it could be all kinds of different values depending on where the system is.